Okay, let's do some examples. Yeah. So for the first order system, it says estimate the time constant of the exponentially decaying function shown below. Okay. Exponentially decaying function would look like this. Let's say you have x of t equals some constant times e to the minus something t, right? Minus, let's say, kt. Okay. In our case, if we use a time constant, it will be 8 times e to the minus t over tau. So what is a in this case? A is, when we just use this number right there, time is equal to 0. We have 8 times e to the 0 minus 0. That's equal to a. Okay. Looking at the graph, that's 1. So this is red from the plot. Okay, red from the plot. So now to find the time constant, it's actually easier than you think. Oh, I don't have a calculator with me, but let's see. So we can pick any point you want. Let's say, should we pick, how about time is equal to, how about 1 second? It's about a little more than like 0.6 at 1 second. So we can just plug in one number. When time is equal to 1 second, we read, how about 0.6, 0. This is totally just made up number, 603. Okay. So I think it's less than 161. Sure, something like that, equals e to the 1 times e to the minus, what's the time? 1 divided by tau. Okay, so let's find what tau is. So let me pause the video so that I can go get a calculator. Okay, so when I plug into the calculator, I get tau to be, okay, so tau to be about 1.98. Okay, so how did I do this? I took natural log 0.603, that's equal to minus 1 over tau, and I solve for the tau. Seconds. So it says time constant is about 2 seconds. So there's another way, okay? Or big or. You can just read from the graph. So what is the time constant? Time constant is when the response is when x equal to when time is equal to tau. What do we know? This is equal to 8 times, which is 1 times e to the minus 1. And we already know e to the minus 1. What is it? Let me see. 1 e to the negative 1. That's 0.68. Okay? So you already know it's 37%. That's the number you're going to memorize. So you go to 37% of the response. So 37% of the response will be about, let's see, that's 3. This is about 3.5. 1. Oh, that's a little too high. Hang on, let me try that again. 5. Okay. 6. 7. How is that? Okay. 0.37, and it's about. Oof, I need a ruler. Let's see. Ooh, are we almost there? Okay, around there. Okay. It looks to be. I think line kind of went up a little bit. Anyway, okay. So the exact answer is, okay. So we find that. Wait a minute. When I go down, this will be your tau. Oh, goodness gracious. Okay, this is tau. So your tau is about, let's say, 1.9. This is just made up number, 99 seconds. Okay, and what was the actual function? Well, I made this function. I actually drew that in MATLAB. So what I plotted was the actual. Okay, so I'm going to write down the actual plot. The real one was x of t equals exp in MATLAB minus 0.5t. Okay, that has a time constant of exactly 2 seconds. 2 seconds. So how do we apply this? How do we apply this finding? So I have a second type of question that says, oh no, what happened? Okay, so I'll just write this one for you. Okay, it says you have an equation that says mv dot plus cv equals, let's say, some f0 times a unit step with the initial condition equals 0. Okay, so now, and then you have a response where v sub t equals, so now you're going to pause the video and then make sure that this is a correct solution, and have a particular solution which is f0 over c minus some constant, like I said, c1. Can I write, how about c1, which is different from the damping coefficient c, times e to the minus, let me see, c over mt is your solution with the initial conditions applied. Apply. Your final solution, v sub t equals now f0 over c minus f0 over c, where c is a damping coefficient. I mean, it doesn't matter. Yeah. The important thing is that the form of the solution is now different. This is the response when you have a step. Yeah, step input. Yeah, step input. So this says estimate the time constant of the step response of a first order system. So this is the first order system. It's a response of the first order system. And can you guess what it's going to look like before I show you the whole thing? No? Okay. I mean, yes, yes, right? You said yes, right? So it looks like this. You have e to the minus c over mt. Okay. And what you do is you multiply by f0 over c. What is it? It's magnification, right? You stretch at the graph vertically. Okay. So this is a stretch in the, you stretch in the vertical direction, okay? And then when you multiply by this, what happened? Okay, it starts with re reflection over the x-axis. Okay, so what happened? So right now, this is the plot we used to have, and it got stretched vertical direction. So now this one is f0 over c instead of 1. So now, after you reflect it, now it's going to cross f0 over c, negative f0 over c, and it's going to look like this. Okay, so this is your time. This is your time. So now, if you add f0 over c to it, okay, to the previous function, what are you doing? Okay, now it's a shift up, okay, it's upward shift. So what happened? So finally, you have a graph like this. Okay. So let's analyze this. Okay. This obviously, okay, as the time goes to infinity, the second part, the exponential function drops out. It becomes 0. This is obviously the f0 over c term, okay, which is 2. Okay, which is 2. I can read that. Now, what's the part that was inverted, that was reflected over the x-axis? So this part minus, that's the gap between f0 over c and the blue line. Yeah. So this one is minus. How about if I just drop the negative, that means it becomes a distance. So this is your minus f0 over c times e to the minus c over mt. Okay? Okay. Or I should just say, let me just say plus. Okay? So I'm going to rewrite this. Rewrite this as a v sub t, which is a blue line, plus f0 over c, e to the minus c over mt. What do you have? You have total of f0 over c. Okay? So is it clear? So I'm going to actually change the arrowhead right there. Okay? I'm going to change it to something like this. Yeah. Something like this. So now, what was the original question? Can you figure out the time constant? So time constant only applies to the exponential function, right? So when you look at the red arrow, initial value was 2, right? So initial value was 2. Was 2. When does it become? What percent was it? 37%, okay, of 2. So 37% of 2 is 1.5. Okay, 1.5. So I need to find the spot where it's 1.5 away from 2. So can you help me with the math? I need to find a place where the gap is. Okay, gap between 2 and the blue line is 1.5. Did I actually do this math right? I'm not sure. Let me try that again. What was it? Let's see. It's 37% times 2. It's 735. Never mind. 0.735. So I need to find a place where the gap is 0.735. Okay, just to make it easy, I'm going to subtract it from 2. I'm going to look for a place where it's 1.26. Oh, actually, it's right here. Okay, so the gap here is this is 37% of 2, which is 0.736 from here to here. Okay, so guess what the time constant is? 2 again. Okay, sorry, I just used the same function. Okay, my piece of t was 2 minus 2 times e to the minus t over 2. I really like 2 for this example. Okay, let me move that one over. Okay, so let's think. Okay, so whenever you have a step response, you have to read actually the 1 minus, okay, 1 minus e to the negative 1, right? Because you have to read the exponential function is actually the gap between the total response and the steady state response. So let's see, let's move on to the second order underdamped system. So it says find the damped natural frequency of the free response of a second order underdamped. Okay, thank you very much. It says the second order underdamped system. I can tell. Okay, so let's find the damped natural frequency. So this is the, why don't we find the period first? Okay, so damped natural frequency really is the actual frequency of vibration. So that's your omega d, omega d. Okay, so how should we do this? Can I just go from positive peak to positive peak? Something like this. So let's see, does it look like this is around, oh gosh, okay, 0.3? How about 0.3? Okay, does it look like it's 0.3? So anyway, this was on the exam in the past, and then you know what people are reading. I'm going to say, what's the period? You know what people are reading? The y-axis. They're reading this value. Okay, so let's not do that. And then here, it looks to be about 1.26. How about 1.27? Okay, okay. I don't think it's quite like 30%. Okay, so I mean, it doesn't look like it's quite 1.3. Okay, so I just, wait, it's a little more than half, right? So 1.27. So to me, it looks like period is about 1.1, maybe 1. Okay, about 1 second, about 0.93 second. Okay, so you can do a little better. Why don't we just get the last peak that I can see? Okay, why don't I just look at that one? Oh, this is hard. I need a ruler. So it's about 1, 2, 3. Oh, I think I might have done this one all wrong. Okay, how's this? No. Okay, don't listen to me. Okay, you do however way you want. Okay, so I'm just gonna delete all that stuff. Okay, so let's see. Oh no. Oh, I think I might have moved that one too. So since I don't know how to undo, I'm just gonna erase that and start over. It's right here. Okay, so that's about, would you say this is about 1, 2, 3, 4, 5, maybe? Okay, maybe. Yeah, so the 3/5 of the way, 4.3. Let's just do 4.3. Okay, I don't have a ruler, I don't have anything. So let's do, oh, the whole picture moved, that's why. Okay, so this is about 0.3, and what did we say this was? 4.3. So period is equal to, what's the gap between 0.3 and 4.3? 4 seconds and divide by how many cycles? 1, 2, 3, the fourth one. Okay, it's 1 second. Okay, 1 second. So what's the damped natural frequency? How do you go from t to omega? It's equal to 2 pi over the period. That's equal to 2 pi radians. Okay, and I'm pretty sure this is correct number, 1 second period. Why? Because, well, I generated this plot and I made sure that all my answer was whole number. Okay, so now let's do, now the rest of them don't have any pictures. Let's find the natural frequency and the damping ratio when the second order roots are -3 plus minus 4i. Okay, so what do you think? Yeah. So if you have a root equals -3 plus minus 4i, okay, what's the characteristic polynomial? Yeah. So really the hard way to do it is I go r. First one is a 3. Minus 3 plus 4i. The other root is r. Minus, the other root is -3 minus 4i. Okay, so you can multiply them, right? So there is a reason why I put parentheses, because I don't want you to multiply like term by term. What I want you to do is I multiply r times r, you get r squared, okay, and r times this whole thing, okay, minus of that, okay. So you should get something like r times -1 times -3 minus 4i. The thing is, I have another term just like it, similar. Okay, so I'm doing FOIL. This is first, this is outer and inner, and between outer and inner term, 4i and -4i will drop out, and then you'll have plus 6r. Okay, is that right? Okay, so now the last term is multiplication of negative times negative, but -3 plus 4i. So negative and negative already canceled. It became positive. So you have -3 minus 4i. So when you multiply those two, what does it become? 9 plus 16, which is 25. Okay, this is a hard way to do this, actually. Okay, why did I find the characteristic equation? Well, because I can get the natural frequency and damping ratio easily from there. How? That's your omega n squared term. And 6 is 2 times zeta omega n, right? So you have omega n must be equal to 5. Drop the negative, okay, solution. Just keep the positive one. And then you have 2 zeta omega n is equal to 6. That means zeta must be 6 divided by 2 divided by omega n, which is 5, so it's 0.6. Okay, 0.6. Should I highlight it? Zeta is equal to 0.6. Omega n is equal to 5. Okay, where did that come from? Right here, by the matching coefficients. Okay, so that's the normalized form of the characteristic equation. So the hardest part of that was actually multiplying those and getting the characteristic roots out. Characteristic equation. So let me tell you another way, okay? This is an algebra lesson. Algebra, should I call it algebra 1? Okay, here, algebra 1, okay? So this is, I don't think you actually learned it in algebra 1. So watch this. You have r equals -3 plus minus 4i. Look, I'm going to move the -3 over. I have r plus 3 equals plus minus 4i. This is the inverse step of deriving the quadratic equation. See, if you were to derive the quadratic equation, negative b plus minus, square root of all that, okay, you actually go backward. So now what I'm going to do is I'm going to square both sides. Okay, so this is r squared plus 6r plus 9 equals, what is plus minus square? That's just positive. Square it, -16. Is that right? 4i times 4i, I times I squared, that's -1. So move over, move the -16 over. So what do you have? Okay, here it is. Okay, So this is a little bit easier. I mean, it's many steps, but usually when I see this, when I see the roots, I can tell what the coefficient would be. Okay, so this is, what is it? This is usually twice the real part, and this is the magnitude. This is the length of the root. Okay, so this one is usually the, not usually, always. Okay, we have -3 and 4. Let me move -3 over down. Oh, it's too tiny. It doesn't want to do it. No, it doesn't want to do it. Okay, I'll just rewrite it. So -3. So this is the real part of the root, and then this is the imaginary part. This is 4. Okay, draw that vector right there, vector. And what's the length? It's 5, isn't it? 3 squared plus 4 squared. So this is the length of R. Okay, length of R on the complex plane. Okay, and then this one, 6 is the twice. Okay, negative 1 times twice the real part. Okay, so now let's continue with the example 3. Example 3 says find the second order roots. So the time constant is 5 seconds and the oscillational period is 3 seconds. Okay, so this one says your homogeneous solution. Again, I should just say free oscillation, or the free response. Okay, the free response oscillates with period of 3 seconds. So you have x free equals e to the minus time constant is 5, so it will be t over 5, right? Then you have a or b, doesn't matter. Okay, some constant times cosine or sine, doesn't matter. Okay, cosine omega d. Okay, what was that period? It was 3 seconds. T plus some phase. Okay, so you have omega d like this. So what is the period? Working backwards, period is equal to 2 pi. It's whatever the time they'll make this term, right? Omega d times t equals 2 pi. So that's the period. So 2 pi over omega d. It says it was given as 3 seconds. So what's omega d? Omega d equals 2 pi over 3. Okay? So here's my answer. Actually, I don't have an answer yet. Hang on. Okay, continue. So now from here, you do know that R. Okay, what is R? The characteristic roots are minus 1/5 plus minus 2 pi over 3i. Isn't that what it says? Okay, if that's your characteristic root, shouldn't that have the form of the free response, the homogeneous solution like this? Yeah. So now I think I have to do the same thing. I need to wait, I just have to say second order root. So I found it. So this is the final answer right here. Okay. What if I wanted to know the system? Okay, what is the characteristic equation, or find the differential equation they'll generate? They'll with free response will do this. Well, then you do have to multiply. So if you remember, what was the trick? Okay, so that was the final answer, but I'm just going to continue a little bit. Okay, so how about if I say how about characteristic equation, okay, or the system model, or the differential equation. So how about the characteristic? So what you do is you find the polynomial, okay, the solution came from. So that's equal to r squared. Let me see, plus twice that, I think 2/5 r plus, okay, it will be 1/5 squared plus 2 pi over 3 squared equals 0. So let me find what that number is. It's 2 times pi, 2 times 3.14 divided by 3 squared plus, I want to do 0.2 squared. Okay, so that's 4.422. So this is equal to r squared plus 0.4r plus 4.422 equals 0. And the system, okay, model that came out of it It'll be x double dot. It could be x double dot, y double dot, theta double dot, whichever. So 0.4 x dot plus 4.422 x of t equals 0. Okay, so this is your system that whose roots, okay, whose characteristic roots are negative 0.2 plus minus 2 pi over 3I, such that the free response will have 5-second time constant, okay, and oscillates with a period of 3 seconds. So it'll be a real pity, okay, if you don't recognize that from the graph, right? Okay. If you have something like this, okay, you fit an exponential function, okay, and then exponential probably is just crosses somewhere here, right? And then see where it crosses. Was it 37% of the initial value, x0, that's x0, okay? So that's gonna be your time constant right there. And how do you figure out the oscillation frequency? From peak to peak, that will be the 3-second period. Okay. So let's see, example 4, the last example. So find the second order root so that the damping ratio is 0.5 and the natural frequency is 2 seconds. Okay. I think this is the easiest one, isn't it? It says damping ratio is 0.5. Natural frequency is 2. Why didn't I just make this an example 1 or something? Yeah. So let's see. So that means you have r squared plus 2 zeta omega n. I'm afraid you're going to have to memorize this. Equals to 0. So you have r squared plus omega n squared. That's 4. And what is 2 times zeta? Is 2 times 0.5 is 1. 1 times 2 is 2. 2r equals to 0. Why don't I just find the root? What is the root? Oh, I think I can do it. I can complete the square, actually. Okay, I see the root right away. That's equal to negative 1 plus minus square root of 3i. There it is. It says to find the second order root. Here's the answer. Okay, so I know you guys are using calculator. Go ahead, okay? Use the calculator. And at least know this equation. You need to save this somewhere where you can find easily. Okay, this is very precious equation.